Okay, so this lecture covers, so we start chapter 9, and it covers this concept of ionic and covalent bonding. So basically it examines how atoms are attached to each other or attracted to each other to make compounds. So basically the two main concepts it covers is ionic bonding and covalent bonding, but there's other concepts covered in this chapter as well that allow us to look at the ionic and bonding and covalent bonding in more detail. So electronegativity, partial charges, formal charges, resonance, core electrons, valence electrons, exceptions to the octet rule, Lewis dot structures, and look at very general bond strength and bond length. So all of these concepts in this chapter you should understand. Okay, so we talked a little bit about core electrons and valence electrons and a little bit about ionic bonding in previous chapter. So just to refresh your memory right quick, so how are valence electrons and core electrons defined? So if we take hydrogen, lithium, and sodium, for example, this is their electron configurations. And in red is the core electrons. So that would be the noble gas core. So 2 electrons is helium, or for sodium, 2 plus 2 plus 6, so that would be 10 electrons, so that would be neon core. So that would be the noble gas core. And so we could write this in shorthand notation, right? Like this, using neon and then 3s1, or helium 2s1. And so the electrons beyond the core then would be the valence electrons. So hydrogen, lithium, sodium have each 1 valence electron, right? And so we can write a Lewis dot structure using that valence electron. So each dot represents the number of valence electrons the atom has. Okay, so, and of course, what does so hydrogen, lithium, sodium, they're all group 1 metals. They all have 1 valence electron. So how about oxygen, sulfur, selenium? So if we did the same thing, so in oxygen, the noble gas core is helium, 2 electrons. Then if you go down a period in the periodic table, sulfur is below it. So if you go down to the next noble gas, so 10 electrons, so that would be neon. So here we have helium, here neon, and then selenium. If we go down well, let's gonna do something different here. So that would be argon, right? So that would be its noble gas core. And so if we write this in shorthand notation, as I've done on the right, so oxygen, helium, and then 6 electrons beyond the core. So those 6 electrons would be the valence electrons. And same for sulfur, 6 electrons beyond the noble gas core, so 6 valence electrons. For selenium, it's a little bit different because now we have d and d orbitals, and if you go down another shell, then f orbitals thrown in. So now we have, if you remember, what's called a pseudo-noble gas core, where we take all of the shells that are full. So the first shell is full, the second shell is full, the third shell is 3s, 3p, and 3d. And so that becomes what's called the pseudo-noble gas core. So if you were adding up the valence electrons for selenium, then again, it's just the S2 and the P4. So those 6 electrons would be the valence electrons. So all of these are in group 6. So that's the easiest way to determine valence electrons, right? Just look at what group they're in. And whatever group they're in, that's the number of valence electrons. So that works for the main group elements. So 6 valence electrons, so we could write a Lewis dot structure, right? The atom with 6 dots around it to represent the 6 valence electrons. Okay, so what is significant about valence electrons is that those are the electrons that are used to make bonds. And those are the electrons that participate in chemical reactions. So the core electrons, for all practical purposes, don't do anything besides occupy space. Obviously, they'll influence the properties of the atom, but they're not going to be participating in bonding in chemical reactions. So it's the valence electrons that do that, so those are the important electrons. So for carbon, what is carbon's valence electrons? Right, well, that's the core, helium, and so it would have 4 valence electrons. And of course, the easiest way is just to look at carbon in the periodic table. It's in group number 4, so it's got 4 valence electrons. And for aluminum, the core would be neon. And so what's beyond the core then would be those 3 electrons. So aluminum would have 3 valence electrons. And beryllium, right, its core is helium, and so its valence electrons would be those 2. And beryllium's in group 2, so 2 valence electrons, aluminum's in group 3, so 3 valence electrons, carbon's in group 4, 4 valence electrons. Okay, so now let's look at the valence electrons in context of how they can make bonds. So if you took an atom of sodium and an atom of chlorine and mixed them, well, what charge does sodium like to be? If you remember from way back in chapter 2, it likes to be +1 charged. So it likes to get rid of 1 electron. Which electron would be that one, right? So the core electrons, nothing is happening to. It's the valence electron, right? It has 1 valence electron. And that's the electron that matters. So sodium loves to get rid of that electron. It has a very low ionization energy. It can get rid of that electron and give it to something else. What about chlorine? What does chlorine like to do? It likes to be -1 charged, so it likes to gain 1 electron. Right? Where would that electron go? It would go there into the 3p orbital because it's not full, right? And so again, for chlorine, that's chlorine. It's core. And so it's got 7 valence electrons. So 3s and 3p, so 7 valence electrons, but it likes to gain one more electron into the 3p orbital. So if you mix sodium and chlorine, that's what's going to happen. Sodium is going to give up its 3s electron, and that electron is going to go into chlorine's 3p electron. And then sodium would become 1s2, 2s2, 2p6, which is Na+. And what else has this electron configuration? That would also equal neon, 10 electrons. So Na+ and neon have the same number of electrons, so they are said to be, if you remember the word, they are isoelectronic with each other. And then if chlorine gains 1 electron, then it becomes that, 1s2, 2s2, 2p6, 3s2, 3p6. And so that would be Cl-. What also has this electron configuration would be argon. So Cl- and argon are isoelectronic. So if you mix sodium and you mix chlorine, that's all that happens. Is sodium gives up an electron to chlorine, but it does so very violently, right? It's a very favorable reaction, so it gives off a lot of energy. Okay. So let's illustrate this reaction using Lewis dot structures. So sodium has 1 valence electron, chlorine has 7 valence electrons. So if you mix the two together, basically what happens is sodium gives up that electron and chlorine picks it up. And now you have Na+ with minus, it's lost 1 electron, and Cl has now 8 valence electrons, so it's now Cl-, so it picks up 1 electron, so it becomes negatively charged. And so this is an example of an ionic compound. So in an ionic compound, you always have a cation, and you always have an anion. Every single ionic compound has a cation and an anion. And so this would be an example of what's called an ionic bond. So sodium and chlorine are not physically attached to each other, right? There's nothing linking them together, but they are attracted to each other, right? Why are they attracted to each other? Because something is positive and something is negative, and opposite charges attract. So that's what an ionic bond is a cation and an anion that are attracted to each other, but not attached to each other. Okay, so let's do the same analysis. So what if we had magnesium and fluorine? So this is magnesium's electron configuration, right? Those are the core electrons. And so this would be 2 valence electrons, right? So what charge does magnesium like to be? If you remember, magnesium likes to be +2 charged. So how does it become +2? Because it likes to get rid of those 3s electrons. So it wants to get rid of 2 electrons. What does fluorine like to do? Fluorine likes to be -1, right? It likes to gain 1 electron to finish the 2p off and to have 10 electrons like neon. So magnesium wants to get rid of 2 electrons, but fluorine only wants to gain 1 electron. So how do you make that work? Well, you need 2 fluorines, right? So one electron from magnesium can go here, and one electron from magnesium can go to the other fluorine atom, and so you would make MgF2, right? So if you mix Mg and F, you need two fluorines to make MgF2 would be the compound that it makes. So magnesium is now going to be 1s2, 2s2, 2p6, so that would be Mg2+, which is isoelectronic with neon. And then fluorine is going to become 1s2, 2s2, 2p6, also F-, which is also isoelectronic. Right, with neon. But again, you need two fluorines for every one magnesium. So if we wanted to illustrate this using Lewis dot structures, so we have magnesium with two valence electrons, and we need two fluorine atoms that have 7 valence electrons. So one of these electrons goes to that fluorine, one of these goes to that fluorine, and you would make an Mg2+ cation. And you would make two F- anions, right? And they would not be physically attached to each other, but they would be attracted to each other. So even though it's wrote like MgF2, you have to recognize it's really an ionic compound, and it really looks like that instead. An Mg2+ cation and two F- anions, not physically linked to each other, but they are attracted to each other. Okay, so how about calcium and nitrogen? Well, what charge does calcium like to be? It's a group 2 metal, so it likes to be +2, right? And nitrogen, if you remember, likes to be 3-. So the formula for the compound it would make would be Ca3N2, calcium nitride. So in order for this reaction to work, so calcium, right, that's its core electrons, argon. And so it only has 2 valence electrons, right? So calcium has, right, 2 valence electrons. But you're going to need 3 of these because you need 6 electrons, because each nitrogen wants to gain 3 electrons. So we're going to need 3 of these. And then we're going to end up taking these 6 electrons, right? And so we're going to need then 2 nitrogen atoms, because what does nitrogen wants to do? It wants to gain 3 electrons there to become 2p6, and then it looks like neon. So that would be N3-, which is nitride, which is isoelectronic with neon. And then calcium, of course, is going to lose 2 electrons. Each calcium will. And so then that would be isoelectronic with argon. Okay, so these 6 electrons, 3 goes there, and 3 electrons go there. And you make two N3- anions and 3 Ca2+ cations. So we would need, so nitrogen has 5 valence electrons, right? Because this is its core, and these are valence. Of course, nitrogen's in group 5, so that's another way again to know that it has how many valence electrons it has. So we need 2 nitrogen atoms, and we need 3 calcium atoms. And then what has to happen is 1, 2, 3 electrons has to go to this nitrogen, and then 1, 2, 3 electrons has to go to the other nitrogen. So you make 3 Ca2 plus, and you make 2 N3 minuses, or you make, so that would be Ca3N2, but you would have to recognize it's really 3 calcium 2 plus cations and 2 N3 minus anions. Okay, so what about carbon and fluorine? So what does carbon want to do? Well, carbon's in group 4, right? So that's core, so it's got 4 valence electrons. So to look like a noble gas, if you remember, carbon would like to be either C4 plus or C4 minus. So either likes to gain 4 electrons here, so then it would be C4 minus, which is isoelectronic with neon, or it likes to lose those 4 valence electrons to become 1s2, and then it would be C4 plus, which is isoelectronic with helium. And fluorine, of course, just wants to gain 1 electron here to become F minus, which is isoelectronic with neon. So the formula for the compound that it's going to make, so you need 4 fluorines, because each one can only take 1 electron, but carbon has 4 electrons to either gain or give away. So it's going to make a molecule CF4, right? But the problem is that carbon does not really want to give up 4 electrons, because when you give 1 electron away, the next one becomes even harder to give away, right? Because now you have, so carbon's got 6 protons hanging on to 6 electrons. It gives 1 electron away. Now it has 6 protons hanging on to 5 electrons. If it gives another one away, now it has 6 protons hanging on to 4 electrons. So every time you take an electron away, the next one becomes harder to take away. And it doesn't really want to gain 4 electrons either to become C4 minus, because every time you add an electron, then you increase electron-electron repulsion. So what carbon would rather do is it would rather share its 4 valence electrons. So this is illustrated here. So we have carbon in the middle with its 4 dots, its 4 valence electrons, and then fluorine with its 7 valence electrons, right? So 7 valence electrons for fluorine. This is its core, helium. So what they like to do is they like to share electrons. So carbon shares 1 electron with 1 fluorine, and it does that 4 times. So if it shares electrons, that's what's called a covalent bond. And so another way you may simply see it depicted is like so. So the 2 dots being 2 shared electrons. So that's a covalent bond. So what does it mean to atoms to share electrons? That means the electron on carbon can orbit carbon's nucleus, or it can orbit fluorine's nucleus. And conversely, the electron on fluorine, the one that's shared with carbon, that one can be orbiting fluorine's nucleus, or it can be orbiting carbon's nucleus. So shared electrons means those electrons are free to basically orbit around either of the 2 nuclei that's in the bond. So you may see it represented like this, you may see it represented like that, or you simply may see it represented like this, where the line, so each line equals 2 shared electrons, or a covalent bond. Okay, and then each fluorine then has 6 electrons that it's not using for anything. So those are what are called non-bonded electrons, or you see them called lone pair electrons. So each fluorine then has 3 lone pairs, or 6 non-bonded electrons. So those 6 non-bonded electrons are basically not doing anything, they're just hanging out. But they are valence electrons, so they could do something. It just depends on if you gave the molecule something to react with, then those electrons could be utilized for something. But just with a molecule of CF4, they're not doing anything. Those non-bonded electrons are just hanging out. Okay, so how do you know if a molecule is going to be ionic or if it's going to be covalent? Well, if it's a metal and a non-metal on opposite sides of the periodic table, then that's typically going to form an ionic bond. If it's two non-metals attached to each other, then that's going to be a covalent bond. So a metal and a non-metal, typically an ionic bond. Two non-metals attached to each other, then it's typically going to be a covalent bond where they're going to share electrons. So let's put that into practice. So let's take these four molecules and predict, are they going to be ionic or covalent? Okay, so PCl3, so phosphorus is here in the periodic table, and then if it's attached to chlorine, so if you remember where your metalloids are, so metalloids are here, right? So those elements in the right, boron, silicon, germanium, your metalloids, everything to the right of that, if you remember, are nonmetals. So these are the nonmetals. So phosphorus and chlorine are both nonmetals, so this is going to be a covalent bond between phosphorus and chlorine. Nitrogen, let's see. So nitrogen is here. Oops, not that. So nitrogen is here, and hydrogen is here. So on the left of the periodic table, but if you remember, hydrogen is not a non-metal, hydrogen is a metal. So sometimes you see hydrogen wrote here on the periodic table as well. So both nitrogen and hydrogen are non-metals, so this is going to be a covalent compound as well. Potassium and bromine. So let's see, potassium is here in the periodic table on the left, and bromine is here. So that's a metal and a non-metal on opposite sides of the periodic table. So this is going to be ionic. And C4H4, so carbon is here in the periodic table, and hydrogen is a non, so they're both non-metals, so this is going to be covalent compound. Okay, so let's draw a Lewis structure for each of these. So this is the method that I use for coming up with the Lewis dot structure. So we'll go through this as we draw these molecules. So we're going to count the number of total valence electrons first. So phosphorus has 5. It's group 5 in the periodic table, right? So 1, 2, 3, sorry, 3A, 4A, 5A, right? 4, 5, 6, 7, and 8. So phosphorus has 5 valence electrons, and chlorine has 7, and there's 3 of those. So there's 26 electrons. So when you draw the structure of this molecule, it better have 26 electrons in it, bonded and non-bonded electrons, or it's wrong. So what we're going to do then is we're going to put the atom, so this is one strategy, put the atom that you only have one of in the middle, and attach everything else to it with a single bond. So let's put phosphorus in the middle, attach the 3 chlorines to it with single bonds. And then what we're going to do is now number 3, we're going to add enough non-bonded electrons to give each atom 8 total electrons, bonded and non-bonded electrons. So we're going to basically satisfy what's called the octet rule. So phosphorus has, each bond is 2 electrons, right? So it's got 3 bonds, so that's 6 electrons. So it needs 2 more to make 8. Chlorine has 1 bond, so that's 2 electrons, so it needs 3 lone pairs. So now that has 8, and this one would have 3 lone pairs. And that one would have 3 lone pairs. So what is the basis of the octet rule? If we go back to looking at it like this, so like phosphorus or fluorine, for example, if it picks up 1 electron, so now right now it has 7 electrons in its valence shell. If it picks up 1 more electron, now it has 8, and now it has a noble gas electron configuration. So that's the basis for this. Same with nitrogen. If nitrogen picks up 3 electrons, then now it has 8 in its valence shell. Right, so you're trying to satisfy the octet rule. Basically, you're trying to give the atom an electron configuration of a noble gas. Okay, so now what we want to do in number 4, so when all of the atoms are happy, that means they all have an octet. Or except for hydrogen. Hydrogen, of course, has 1 electron and it only wants 1 more to look like helium, so hydrogen only wants 2, but the other elements want 8. So when they have 8, they're happy. They have an octet, they look like a noble gas. So we want to count the number of electrons once everything is happy. So once we have enough bonds and dots around everything to make 8, and see if we have the right number of electrons. So we have, let's see, so 1, let's not do that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lone pairs times 2, that would be 20. And then bonds, we have 2, 4, 6 more electrons, so that would be 26 electrons total, which matches what we're supposed to have. So that's the structure of PCl3. Everything is happy, we got the right number of electrons. Okay, so on this rule number 5, so what if we didn't have the right number of electrons? What if we had too many electrons? If we had too many electrons, then that would mean we need a double bond or a ring in the structure instead. So we would erase 4 non-bonded electrons and we would add a double bond or we would add a ring. And in the next lectures, there's examples of that. Or if we counted our electrons, say instead of 26, we had 30, if we had 4 too many electrons. If you have 4 too many electrons, then that means you either need 2 double bonds, or you need 1 triple bond, or you need 1 ring and 1 double bond. And again, there's examples of that in some of the other lectures. Okay, so let's take this example, NH3. So nitrogen has 5 valence electrons, hydrogen has 1, and there's 3, so there's only 8 electrons to build the molecule. So then we go to number 2, we take the atom that there's only 1 of, which is nitrogen in this case, and we put it in the middle. And then we attach the other atoms with a single bond. So now we've done number 2. And now number 3, we add enough non-bonded electrons to give everything 8, right, except hydrogen, which only wants 2. So hydrogen's happy, it's got 2 electrons, so nitrogen needs a lone pair, now it's got 8. So nitrogen's happy because hydrogen's got 2, nitrogen's got 8. Count our electrons, there's 3 bonds, that's 6 electrons, 1 lone pair, that's 2 more, so that's 8 electrons, which is what we're supposed to have, so that's the structure of the molecule. Okay, how about KBr4? So this is supposed to be ionic, right? So if you remember, potassium wants to give up 1 electron. It has 1 valence electron. Bromine has 7 valence electrons. It's in group 7. And so potassium is going to give up that electron. So it's going to become K plus and Br minus. And it's going to be an ionic compound, right? So you don't want to do this, because that would be totally wrong, because what does a line mean? A line means a covalent bond. It means it's sharing electrons. So this is not covalent, this is ionic. And you don't want to do this, because if you draw them too close to each other, to me it looks like you're trying to tell me they're sharing electrons. And right, they're not sharing electrons. So you want to draw them far enough apart that I can clearly tell that you're not trying to share electrons between them. You have a cation and you have an anion that are not physically attached to each other, but they are attracted to each other. Okay, so that would be the Lewis structure for KBr. And then lastly, so C4H10. So carbon's got 4 valence electrons, and there's 4 carbons. Hydrogen's got 1 valence electron, and there's 10 of them. So that would be 16 plus 10, so that would be 26 electrons to build this molecule, right? Okay, so this one's a little bit harder than the others because we can't apply number 2. We don't have an atom that we just have 1 of that we can stick in the middle. So this one's a little bit harder. So how do you solve a problem like this? Well, the way that I solve most problems is trial and error. You just start trying stuff until you can find something that works. So the easiest thing to do here is, well, let's just attach the atoms that can make more than 1 bond, right? Hydrogen can't make more than 1 bond. So if you ever put 2 bonds on hydrogen, you know it's going to be wrong all the time, because that would mean there's 4 electrons on hydrogen. And you can't put 4 electrons on hydrogen, you can only put 2, right? Because hydrogen is 1s1, and it only wants one more electron to become 1s2. So hydrogen can't have two bonds. So if you put two bonds on hydrogen in this class, or if you go into organic chemistry and you put two bonds on hydrogen, it will be wrong 100% of the time. Right? Hydrogen likes one bond. So a carbon can take more than one bond. So let's string the carbons along, and then let's take the hydrogens and attach them with one bond. So carbon wants 4 bonds, right? So now it's going to have 8 electrons around it. Right? Carbon has 4 valence electrons, so it can share those 4 to make 4 bonds. So the 2 N carbons want 3 hydrogens, the 2 middle ones only want 2 hydrogens, so that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So that's the right number of carbons. That's the right number of hydrogens. Is it the right number of electrons? Well, how many bonds are there? There's 1. Well, let's not do that. Let's not make the picture too messy, but there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 bonds. So that's 26 electrons. So carbon's happy. Each carbon's got an octet. Hydrogen's happy. Each hydrogen has 2 electrons, 1 bond around it. 26 electrons is what we're supposed to have. So that's the structure of the molecule. Right. Now you could have also come up with a different structure. You could have come up with, you could have attached the 4 carbons like that, and then if we attach 4 hydrogen, not do that. Then if we attach each hydrogen, each carbon to give 4 bonds. Now the one in the middle only wants 1 hydrogen because it's got 3 bonds to carbon. So if we do that, that is also C4H10O. Each carbon's got 4 bonds. Each hydrogen's got 1 bond. That's 26 electrons. So that's a perfectly valid structure as well. So in this class, if I gave you C4H10 and asked you to draw a Lewis structure, I would accept either one because either one is perfectly fine, but I wouldn't expect you to necessarily have to come up with both of them. If you go into organic chemistry, I would expect you to come up with both of them, right? But for this class, if you can just come up with one Lewis structure that works, I'm happy with that. Okay, and then lastly in this class, this lecture, just wanted to point out that some compounds can have both covalent and ionic bonds in the same molecule. So you can have a mixture of covalent and ionic bonds. So an example would be sodium acetate. So if we had that and we came up with a Lewis structure. So if we come up with this Lewis structure, then, so if we counted our valence electrons, right, 2 carbons, 4 electrons each, 3 hydrogens bring 1 electron each. Oxygen brings 6 electrons each, and sodium has 1 valence electron, so there should be 24 electrons in that molecule. So this is a good Lewis structure, right? Each carbon's got 4 bonds. So a double bond, we'll talk about a double bond in the next lecture. But this has covalent and ionic bonds, right? Every single line. So line, 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 right? Line, line. Both of those lines, those are all covalent bonds. But this would be an ionic bond, right? So oxygen's a nonmetal. Sodium's a metal. So that's going to be an ionic bond between oxygen and sodium, but between oxygen and carbon, carbon and carbon, and carbon and hydrogen, those are all covalent bonds. Right, so you would not want to do this because if you draw a line between oxygen and sodium, that means covalent bond, and it's not covalent. It is ionic. Okay, so we will stop there.